So the portion for today is going to be reviewing for 6.2 and 6.3 for what we started. At the end, probably like the last 5-10 minutes of this video, I'm going to do 2 problems for finishing up 6.3. We started one of them. I did something I told us not to do. So great job on my part. I didn't read. I can actually show you. On my notes, I have a nice big other page. It's somewhere. Ah, yeah. I have it nice and highlighted. It says stop. I didn't read that. So I'm going to fix that part and actually listen to my notes. And then from there we'll do another problem. That way we'll have 6.3 primarily done. This is going to be mostly a review of verifying trig identities, solving a trig identities. So if we keep practicing those, I'm going to give us something tomorrow to work on over the weekend. So you'll have an entire weekend to do all the different properties and identities we've used. You'll hopefully be good with the more practice. So with that said, I'm going to switch over. I'm only going to briefly discuss the equations for sum and difference, primarily because we only use these to derive the double and half angles. So for people who were not here, this is something we should be putting in our notes. If you were, here, you already have these in your notes. We already went over them and kind of just like in depth. We had discussed these at least on Wednesday. So these are the sum identities. And then we have difference identities. So I'm going to start with cosine. For cosine, if we have 2 angles, say x plus 2x, or in this case a plus b, we know that this is going to be equal to cosine of a times cosine of b plus, adding is opposite for sine, for cosine. So for cosine, if we have sum, we actually take the difference. Then the difference for cosine, well, if we have sum, I'm saying the wrong word. I'm saying the right word and then not putting the right symbol. Difference, not sum. So we want the opposite sign. We're going to keep the same form. So it's going to be cosine A times cosine of B minus sine A plus sine A. We want the opposite sign for cosines, sine B. So again, to point out, for cosine, we want the opposite sign. So it's always going to have the form cosine A, cosine B, and then sine A, sine B. If it's A plus B, it's going to be the cosines minus the sines. If it's A minus B, it's going to be the cosines plus the sines. We then also looked at the sine sum and differences. So sine of A plus B. For sine, we're going to keep the same sign, but the multiplication is going to be a little different. Over here, we get sine of A plus B is equal to sine A times cosine of B plus sine B cosine of A. Hold on 1 second. And then on the opposite side, so for the difference, we're going to keep the form for the trig functions. So I have sine of A minus B. is going to be sine A cosine B. And then instead of having plus, I match my sign, so I'll have minus. The last one we had discussed, well, we have sine, we have cosine, we also need tangent. Tangent is a little bit different. So I'm just going to give us tan. So tan for sums. We could also think of this as sine over cosine, if you want to do it that way. Or we could write it as tan A plus tan B over 1 minus tan A times tan B. The difference we're just going to switch our signs for tan. So tan A minus tan B all over 1 plus tan A tan B. Again, we note that we could optionally simplify tan of A plus B to sine of A plus B over cosine of A plus B, and then solve using the properties for the sum identities for cosine, the sum identities for sine. Now I'm just going to do one quick example with these. Erase this bookmark, change my defaults. So we're going to look at verifying that 3 sine 4x is equal to 3 sine x cosine 3x plus 3 sine 3x cosine x. Now what's nice about this is the fact that we have just the coefficient times our sine. And I can easily split up this sine of 4x with a sum of, well, x plus 3x is 4x. So since we're working with just a variable and a coefficient, it's easy to split up instead of having to find our angles. This is usually what we're going to be seeing, just because we want to be able to identify things. We did do some problems where we needed to find specific angles. If we had, say, sine of 15 degrees, well, I know I can write sine, or I can write 15 as 45 minus 30. So this is really sine of 45 minus 30. And then we just applied our rules and just plugged in the values from the unit circle. So over here, I can rewrite this as, I'm going to use this in green. This is 3 sine of x plus 3x. Order kind of matters. If we had subtraction with sine, it'd be more important. For here, since we have addition, we know that we're going to want addition since sine of a plus b gives us a addition. And this is going to be the same. I don't really need to write that down again. Well, now I have 3. This is just a coefficient. It's not too important right now. We can just look at sine of x plus 3x. So I'm going to have 3 distributed to. This is sine of a. Here's my a. Here's my B. So I have sine of A times cosine of B plus sine of B times cosine of A is equal to, just bring this down again. And now what I do is I distribute my coefficient back in. So I would just have 3 times sine of x times cosine of 3x, and 3 times sine of 3x times cosine of x. So this gives me 3 sine x cosine 3x plus 3 sine 3x cosine of x, which is equal to what we wanted. So this is true. This is an identity. Okay. So this wraps up 6.2. I have my wrong colors. 6.2 was really just knowing these 6 identities. That's it. We then used these to derive 6.3, which is much more important, as 6.3 gives us our double angle and our half angles. So to start, we had looked at, say, sine of 2x. We ended up writing this as sine of x plus x, and then we used our sum identities to be able to derive the double angle identities. So this was sine x cosine of x plus sine x cosine of x, which is just equal to 2 sine x cosine of x. Okay. So for 6.3, this is double and half. I'm just going to remake our table that we had. So for sine, I just wrote this one out. It is sine of 2x is equal to 2 sine x cosine x. For cosine, we end up getting cosine 2x is equal to cosine squared x minus sine squared x. And for tangent, we have tan of 2x is equal to 2 tan x over 1 minus tan squared x. An easier way to think about this, though, is just as sine of 2x over cosine of 2x. This will usually save you time with problems. I put those in parentheses so we're not confusing them as sine squared. Now, I had made a mistake earlier in using applications wrong for cosine. I note that, oh, actually we didn't get to half angles, correct? We did not. Or we did. No, we did. So I can rewrite this if I recall my Pythagorean identity. So I had cosine squared x plus sine squared x is equal to 1. So I can make substitutions based on what I'm looking for. So if I want to replace my cosine of squared x, if I want to simplify into terms of x, I could have, this would be, well, 1 minus sine squared x minus sine squared x, which is equal to 1 minus 2 sine squared x. The other option is to substitute for sine, in which case, well, we would subtract the cosine from both sides. So then this is 2, or 3 really. And here, well, we keep the cosine. Square root of x, and then we plug in for sine. So I have minus, this is 1 minus cosine of x. I distribute my negative. So it's going to be cosine squared x minus 1 plus cosine of squared x. So this is just equal to 2 cosine squared x minus 1. So these are the double angle identities. So these are things that you already have written down in your notes, and that we're going to, you get these on the final, you are provided with these ones. So these ones you don't have to remember how to derive, you just have to remember how to use them. So that's why we went through them kind of quick in class. We then also had half angles, which means that we'll have half inside of the trig function. So I'm going to default this side sine, draw my line, these are half. So for sine, we had sine of x over 2 is equal to plus or minus, depending on the angle, square root 1 minus cosine of x over 2. If you're given an angle that fell in quadrants 1 or 2 for sine, it would be the positive. If your angle fell in quadrants 3 or 4, it'd be the negative. The same idea is going to hold for cosine. Cosine of x over 2 is going to be equal to plus or minus the square root. For cosine, if you're in quadrants 1 or 4, it'll be positive. Quadrants 3 and 2 will be negative. This is going to be 1 plus cosine over 2. And then our last one, which is really the easier one to work with, is for tangent. For here, there's a couple of forms. Honestly, I'm only going to write the easier ones, just because the first form we will hardly ever use. So I'm going to save that one for last. So our first form is sine of x over 1 plus cosine of x. Oh, not 2x. This should be tan of x over 2. Then our second form is 1 minus cosine of x over sine of x. Our third form, if you ever wanted to, if you needed potentially a square root for some reason to cancel out square roots, though you probably won't see problems like that, just a heads up. Third form is 1 minus cosine x over 1 plus cosine of x. Okay, so these are the actual formulas for double and half. We should have these written down. In your notebooks. They're incredibly important. You will get them on the test. You just need to know how to apply them. Okay, so let's look at an actual identity. We did this one in class, and then we're going to get into the one that we didn't do, and then we will be good for today. So we're first going to verify sine x minus cosine x squared equal to 1 minus sine 2x. Okay, we have two ways to approach this. We could start with the left, or we could start with the right. I'm first going to start with the left because I have a nice square, and I know that this is just going to give me sine squared, so I have a minus b all squared, so I'm going to get a squared minus 2ab plus b squared, so this is going to be sine squared x. Here's my a, here's my b, so this is my a squared minus 2 sine x cosine x. Here's my 2ab plus cosine squared x. Here's my plus b squared. This is all still equal to 1 minus sine 2x. Alright, if we look, we have to think back again, and this is going to keep coming up, the Pythagorean identity. I have a plus cosine squared and a plus sine squared. Pythagorean identity tells us sine squared of x plus cosine squared of x is equal to 1. You need to have this memorized. This should be stuck in your head. If it's not, that's a problem. So this simplifies to 1 minus 2 sine x cosine of x. And we want to show this is equal to 1 minus sine 2x. Alright, I'm going to draw us back really quick to our double angle for sine. Sine of 2x is equal to 2 sine x cosine x. I have 2 sine of x cosine of x. So this is just 1 minus 2 sine, sorry, not 2 sine, 1 minus sine of 2x, which does indeed equal 1 minus sine of 2x. So this is a trig function. This is true. And now, this is where we had left off last time we met. This is where I didn't read my note that told me to stop and to approach the problem differently. So, I'm going to scroll over here. Reset my colors. Go to my brush. Okay. Next, we're going to verify cosine of 3x is equal to 1 minus 4 sine. So this is something we should be practicing along with, cosine of x. The first step we did was sum identity. We know 3x, this is x plus 2x. So, I'm going to make sure this is in order. We're actually going to write this as 2x plus x to reduce the number of operations we need to do. You get the same answer if you did the other way. You just have to distribute negatives appropriately, which would take more time. So over here, we're going to have cosine 2x plus x. I'm not going to bring this down yet. Well, I know this is the sum identity for cosine. Cosine is cosine of 2x times cosine of x. For cosine, it's the opposite sign. So I'm going to have minus instead of plus, and then sine A, which is 2x, sine B, which is x. Cool. I now have double angle properties. I've got a sine of 2x and I've got a cosine of 2x. Alright? So let's apply this. I've got over here, I'm going to flip to my double angle properties so I don't have to keep scrolling. Cosine of 2x is going to give me cosine. This is where I went wrong, and this is where I'm going to repeat it, but I'm going to stop this afterwards. So this is cosine of x minus sine squared x. This is in parentheses, times cosine of x. And that's going to be minus, well, sine of 2x becomes 2 sine x cosine x sine x. Alright, I'm actually going to do this one differently after. I'm going to simplify the right side because the right side is fine. This is 2 sine squared x cosine of x. If we look back on the right side, we only have sine squared of x inside our parentheses. So I don't want to have this cosine squared of x. I know that I can get rid of the cosine squared of x if I use property number 2 instead. So this is just substituting cosine squared of x with 1 minus sine squared of x. So I'm going to hop on back over to the problem. So instead of using this, if we did start with this, it's fine. We could then just go and I forget what I'm trying to say. We can then just go and substitute for cosine squared of x, which we can still do. If you recognize the property right away, that's also fine. If I didn't recognize the property right away, I would then get, well, cosine squared of x is equal to 1 minus sine squared x. And I'm going to keep the minus sine squared x. This is where I got stuck because then I kept trying to use the next step, which was wrong. So now this, inside the parentheses, will simplify to 1 minus 2 sine squared x times cosine of x. And then minus 2 sine squared x cosine of x. Alright, here we need to do some algebra. I have a term, which is 1 minus 2 sine squared of x times a second term, cosine of x. I have a term, negative 2 sine squared x. This is A, this is B, this is C, and well, this is also B. So I have a like term, which is cosine of x. So I can factor that out. That's going to give me, I'm going to start with my inside, so A, so 1 minus 2 sine squared x, and then plus C, which is a minus 2 sine, so this is A plus C all times B squared x, and then my like term is cosine of x. So now we're starting to see something that looks pretty much what we need. Right, we're bringing this down because I can combine my like terms. Sorry, not like term, common factor. Either B is common factor, not a like term. If I can combine my like terms, which is 2 sine squared of x and 2 sine squared of x, the term in this case is sine squared of x. Well, this is just 1 minus 4. 2 minus 2 is 4. So negative 2 minus 2 is 4. Sine squared x times cosine squared of x, or cosine of x. And this is what we wanted. We need to verify, I should say, that cosine 3 of x is equal to 1 minus 4 sine squared x all times cosine of x, which with trig identities in algebra we got. So this is, I'm going to choose a fun color right now. Let's do light blue. This is true. Okay. Alright. For the last practice and video, and then I'm going to have people do one on their own for preparation for tomorrow, and we'll review that tomorrow to start. We're going to look at a half angle one now. So I'm going to verify, let's go back to my default, cosine squared x over 2 is equal to tan x plus sine x all over 2 tan x. Alright, now question is, how can I rewrite, because I don't have identities for cosine squared in a half angle. I have identities for cosine in a half angle. So how can I rewrite this? Well, this is just cosine x over 2 all squared, and then I'm just going to copy this down. So quote it. Now I know what the half angle for cosine is. If I look back in the notes, half for cosine is plus or minus the square root 1 plus cosine x over 2. So I'm going to keep this visible while I write this. So plus minus square root 1 plus cosine x over 2, all squared. This is equal to, well, we haven't changed anything on the right yet. Taking the square, or squaring, I should say taking the square, squaring a radical cancels the radical. So for here I'm left with 1 plus cosine of x all over 2. I don't need the plus minus because squaring will always give me a positive. It's going to equal, I'm going to actually write it down now, tan x plus sine x all over 2 tan x. Now we have something else to work with. Alright, for starters, let's do some algebra and split up our numerator. So is equal to tan of x over 2 tan of x plus sine of x over 2 tan of x. And so really, if I want, I can actually, I'm going to make this even easier. Or actually, no, I'll leave that. That's fine. I'll leave that for now. Alright, on the left, if we notice, well, I have a tan and I have tan. So these cancel out, which just leaves me with half. And then I have plus, well, sine stays the same. So sine won't change. But then my 2, so I'm going to write this as 1 over 2. 2 tan of x is going to be the 2 stays. Tan becomes sine of x over cosine of x. Well, now I would multiply by the reciprocal to cancel out the fraction and a fraction. Cosine of x over sine of x. In this case, these will go away. These will cancel. And then I have sine over 1, so sine cancels the sine, and I'm just left with cosine. So it's equal to half plus cosine of x over 2. I want to bring this down. 1 plus cosine of x over 2. And this here, I can take out the common factor of a half. So this is equal to, or I can even just combine the numerators. Actually, that's the right way to do it. 1 plus, since they have the common denominator, cosine of x all over 2, which is what we wanted, so this is true. Alright, for tomorrow, I want you all to try cotangent of x minus tangent of x all over cotangent of x plus tangent of x. This one is just simplifying, you're not verifying. It's very important to make sure you write things in terms of sine and cosine to start with this, and then make sure you can actually add and subtract numerators by having a common denominator. You are only going to have one term in the end, so I'm going to tell you, you should be able to get to cosine of 2x. So simplify this guy to get to cosine of 2x. Do that for practice for tomorrow.